are going to be piling in. Last several times folks came in. Most folks showed up within 5 minutes after the meeting started. And I have to manually admit them in an effort to keep the spam bots down. So that's just sort of what's going on. And new this go around is I'm recording, and I'm recording right now. So I hope you're all okay with that. And I'm going to put the make the link public as soon as I can. And okay, I'm doing too many things at once here. And if you don't like that, you need to log off. And then you can look at it later if you want. Gotcha. Oh, another one. Yeah, so welcome to the Coffee Compiler Club. Here's my coffee. No set agenda. I'm looking for people to talk about compilers and language implementations and runtimes with. I'm recording the meeting right now. I'll put the link on later. If you're not good with being recorded, bail out now. Other than that, we go for an hour or until we get tired. So far, it's been at least an hour, and topics run all over the map. So anyone can ask a question. See, my audio volume is clipping a bit. I can't do a whole lot about that. That is up to the beer compiler. What time zone you're in. I ask that you remain muted unless you're going to ask a question, because we can't have 20 people with open mics or we'll get too much background noise. Other than that, be respectful, and all things are good. You can hear me typing, which might be messing with my mic too, and that's just me. UTC +1. Okay, well, welcome aboard here. I guess it is about that time, huh? So I guess I don't have any agenda to start with. Somebody last time had a question, and I said that's a good question for next time. And I think that person is here. Not certain yet. Otherwise, if anyone wants to start the ball rolling, or I'll throw out, open question from last go around. So Cameron and I went back and forth. So I'm going to start the ball rolling, and only because, everyone's all being quiet. So Cameron and I went back and forth on the value of null in a language. And Cameron's take was, and he's right there, so he can correct me if I'm wrong, was that it's a cause of problems and should be removed from the language directly. And you have to have a way to deal with not a thing if you don't have null in the language. A bunch of languages make this choice, including Scala and Elm, where you have unit type or maybe or result types, which represent a thing or not a thing, as a way to get away from having null in the language. And having null in the language does give you this funny value, which is kind of sort of a subtype of all other types.
Right, that's the problem.
I come around from a different view, which is null in my head. I've lived with it all my life. It seems a very convenient abstraction to represent not a thing. And, it's woven throughout all the code that we've ever had for the last 40 years. And I think there's an answer is to live with it, but at the same time, make it more safe and livable by automatic null checking and or null elimination and or compiler type support that says this is null, this is not a null, and you're not allowed to, for instance, load a null value. The compiler knows darn well that it's null or could be a null and demands a test beforehand or not because it's inferred it's not. So it's sort of a different take. And I'm just trying to open a conversation. I see Cameron turn his mic.
Yeah, the problem isn't so much that null exists, it's that it can be assigned to anything. And that's the challenge, is that it...
And I have no sound from you, Cameron, although I see you. That's probably my fault. Say again?
Can anyone else hear me?
I can hear you now. It's my bad.
Oh. I was saying that the problem isn't the existence of null. The problem is that null is a subclass of anything. So you can assign null to anything. And because of that, the language, the compiler, the runtime, they all have to be aware that null could be anywhere. So it just, we've lived with it in C, but there's no reason in my opinion to continue to live with it in a new language.
So you're unhappy about it because it's a subtype and it makes the typing system nasty, or because
right,
you have to put checks for it everywhere because it can be anywhere?
Yeah, both.
Both. Okay.
It just violates. It's like it carves out a special rule that touches every aspect of the language and every aspect of the runtime. I mean, you wouldn't, for example, let someone assign a string to just any type. Why would you let them assign a null to any type? I mean, why have a type system if you're going to have a null?
Okay. Yeah, I solved that problem a different way, maybe.
I really like the concept of like optionals, or where you're forced to, if something can be something or null, and then you're forced to handle it every case you're dealing with that type.
Yeah, that's a version that says, here's one way to make null more polite as a thing. And I think both of what we're talking about do something along that front. You have to do something there, because you can't just have the, throw an MPE and die, right? That's right. The current Java standard is that you get a polite exception, but you get an exception. And the C standard, of course, you just crash and burn and whatever, security leak and everything bad happens. Java turns the bad security into you get a crash and burn, you get a polite one though, you get a null pointer exception. And languages like Kotlin and Scala and Elm say, we're going to tell you that you have to go do something so that you don't get the NPE. Instead, you're forced to do handling. Now, maybe you don't want to do handling because you think it can't happen and the compiler can't prove it can't, but you want to do the minimal amount of handling just to get past the damn type checking, right? I don't know. What's the right good answer there? I'm sorry, I'm still managing people coming in too here.
So the last few years, I've been alternating between developing in Python and Scala, and the one comparison that I have between a language that promotes that has nullable and one that uses the options that was just mentioned is that when things do go wrong with Python, is more often than not, I'm looking at logs, looking for null pointer exceptions. Whereas with whenever I've been debugging Scala applications, it's been more focused on business logic going wrong, as the null bit has been handled one way or another, so you don't see it in your logs. I just thought I'd put that comparison out there as just one observation from when things go wrong of the different ways that I would have to search to find a problem.
So what I heard you say was Scala's handling of null via using options, the optional lifts the problem space up from some low level, it crashed or didn't, to some sort of towards the business logic side of things where some higher level concept blew up, didn't get it right.
Yeah, that's how I felt my debugging life became. the difference between the two paradigms. Yeah.
Yeah. I think Helm had a similar approach with
Yeah.
maybe instead of optional. It's just a name change, and the same kind of deal. Sometimes it was very convenient, and sometimes it was a pain in the neck to deal with null in cases where it just wasn't going to happen anyhow. But I had to have a dealing with it. There, I think, in case of Elm, the shortcut syntax for saying do nothing with null except propagate the null along, because that's not going to happen, was less convenient, and there are easier ways to do it. And I think Scala probably got an easier approach there.
But Cliff, isn't part of the reason that you're not too worried about it is that the work you're doing right now is based on deducing types automatically, and you think you can deduce which ones could be null, right?
Yeah, totally. So, this is any kind of type inference with null, and Kotlin does this too, right? I'm sure Scala does a fair amount. You do type inferencing on null. So most of the time you know that it's not a null, or it could be, and it's only an issue where it could be and you're wrong. The type system's weak, and the programmer knows it can't be, and that works right until the programmer's wrong and the type system's right. Right? So yeah, you need to have a shortcut that's like convenient to use.
It's interesting because it kind of actually brings up one of the topics I was going to ask you about today. Which is backtracking. I think that's the right term. So let's say you're way down in a branch, and somewhere halfway down the branch there's reflection, and another 20 methods there's another reflection, and each one of these methods is returning a value. So it's like that value gets returned the whole way back, and where it's getting returned to, you think it's an int, right?
Okay.
And everything you've ever done, every billion operations every billion iterations you've done so far, it's been an int, right? And now it comes back as a null instead.
Right.
So all your code optimizations are built around knowing it's an int, and you couldn't have predicted because of reflection.
Int's a poor choice because null has a value in int that's very obvious. So everything says I have some sort of object, node, person, struct thing, and now I have a null.
I'm talking an object system, so let's say string instead.
Okay. Yeah, fair enough. Yeah. Right.
Our int is an object, so.
Right. Yeah, and I have a performance bias, so my ints are raw all the way down the line, and they support the null in all the right ways.
Sure.
But I'm sidetracking. So your question is, what do you do with code optimization as opposed to typing? That's what I'm hearing.
Right, because you have a long call chain, and the way I think Hotspot dealt with this was that it actually knows the structure of the code and the locations on the stack for each type and so on, so it can actually replace the code on the fly, kind of reforming the stack around the new optimizations.
Yeah, so this is a code optimization issue and not a typing system question at all. And it's just what do you do when your types change out from under you? It has nothing to do with null. The hotspot will know what the typing system claims can happen, observe what has happened in practice. If the types are fixed at various points where it's interesting in practice, a call site where the this pointer is known. It could be one of a variety of types, but happens to only be string ever since I've ever seen it. Then Hotspot put a check in that says it's still a string and generate the code as if it's a string now. So Hotspot essentially puts in an assertion saying it's a string. If the assertion fails, then it has to go back and reprofile and reject. Does that answer your question?
Yeah, it's kind of part of it. The amazing thing to me is the fact that it reprofiles, it rejits, but it's got across 100 different threads, it's got 10,000 stack frames, all of which have data in them, and now the code changes on the fly.
It's the whole 0, 1, infinite, right? There's no hotspots. There's one hotspot. There's an infinite number of them. There's one stack frame. There's no unicorns. There's one cliff. There's a billion stack frames. So the computer does a million fine.
What I meant is it has to actually restructure the stack frames.
No. Well, yes. If you have to, if you've done down a certain path, there is a path where you restructure stack frames. Yes. Yes. And that's called deoptimization in hotspot lingo, and that's where he reverts the optimized compiled stack frame like you get out of a C compiler to interpreter frames, which are basically instances of the abstract virtual machine that represents the bytecode engine that Java runs on. It has nothing to do with x86 hardware at all. It goes through an implementation of the bytecode engine for the stack frame layout. And then it carries on in the interpreter while it's reprofiling.
And then it can go back to running the optimized.
That transition goes both ways. Once you've interpreted for a while, you want to stop and roll into compiled frames again. And the forward direction is almost always done at a call site. So some interpreter frames will remain on the stack, and the stack's mixed, interpreted, and compiled frames.
How hard is that?
I like to claim it's not rocket science, but it's freaking nitpicky as all hell. And there are a lot of funny cases that are corner cases that don't show up very common. So there's careful debugging technology that you want to weave into your process for building this to help you find and catch all the corner cases. But there's totally a finite number of them. And once you got the last one, you're done. It is a nitpicky piece of, pain in the neck. But like I said, it's not a long tail distribution. It has a longer tail that goes to 0, and then it's done, and it's all over. So it's a solvable problem in that sense.
You busy this weekend?
I charge for hours for fun. This is free because I'm having fun. If you want me to do it, there's a bill. If you want me to to tell you what to do, that's a much smaller bill.
Understood.
You need to have some comfort with low-level x86 bits and bobs. Stack layout. On an exception, he does stack puke, right? He barfs all over your stack, and you're not allowed to look at the barf. Many processors have similar behaviors. There's Windows on some processors and not on others. There's ARM has different calling conventions than x86 in a variety of ways. Stacks go up, stacks go down. All these things can all be worked through fairly straightforwardly. It's a lot of nitpicky detail, but a finite amount of it.
Any experience with LLVM in this space?
No, I've never touched LLVM. It was the wrong compiler for what Hotspot needed. And I think even today, it's not the right compiler. I know there's some folks, Azul in particular, is trying it.
Right.
Maybe. It's not my...
Well, Azul and the Grail project as well both use LLVM.
I thought Grail was doing their own code gen all the way. They have a version that uses LLVM?
They use LLVM to do bitcode interpretation to do native calls. So you can call bitcode from the multi-language runtime.
Okay.
That's what they use LLVM for.
Okay.
Yeah,
okay.
they also have an experimental backend using LLVM. They have their own code gen, but I think they have the backend using LLVM to get new platforms easily.
Yeah, right, totally. Yeah. Yeah, the effort to port Hotspot included the effort to port the code generator, which was a non-trivial. So you'd love to have picked up, CodeGen for GCC. LLVM wasn't really stable or the right target remotely when Hotspot first came around 25 years ago. But
it kind of didn't exist at the time.
Exactly. Well, it came around while Hotspot was still sort of on a good, strong roll and picking up new platforms. But even when it first came around, it wasn't. It didn't have the right features you needed out of the CodeGen. And neither did GCC. So Hotspot ended up doing its own portable backend, and that meant porting Hotspot. You had to port the backend CodeGen. You had to deal with all that.
Yeah. So back to the type system on the null side. I put it into the chat, but yeah. The way we handled null is we just created it as an enum.
Yeah, I think Scala does the same thing. I've seen that. For me, I'm using a lattice theoretic approach, and null is outside the lattice, oddly enough, but it can meet with anybody and make something in the lattice. Here, I'm doing people management for a second. Yeah. Yeah, so, and in my version world, then null's not really a subtype of anything. It can be added into anything, if you will, to make a null or not string, string or null, which is a property of pointers that you propagate throughout the system, and at the use sites, I better have discovered it's not a null, or you have to put a test in, or you have a runtime, you have a compile time type error that you're missing a null check. So it's I don't know. I claim it's equivalent, although the implementation is totally using the 0 bits as a null, and you'll have to put in checks the same as an option would with a, it's got something or it's not a maybe, or it's not a maybe, or whatever your language jargon of choice is. As soon as you have a union type, so you put down a union type. As soon as you have a union type and you come to a use site, you have to pick the union type. So actually, I'm not currently supporting union types. I've gone back and forth on this. I'm kind of supporting them for overloaded function calls only, where the type of the function call is the overload set, and that's a union type. But I'm not otherwise doing union types. It's not being yes, it's not a bottom type. I'm reading the chat. Yeah, so it's a lattice theory. There are a lot of places where I have not what I would call a union type, but a structural adjacency type, like the members of a field of a struct. The field members of a struct are all parallel and adjacent, but they're not a union type. They all have each their own type. So your pointer has the property that it's null or not, has the property that it's string or not, property that it's this or not, or that or not, or whatever, has all those all at the same time, all basically done as a bit set. And then at the time you hit a load or store, if the null bit's in there, then your null's allowed, and that's not allowed at a load or store, and so you have to remove it by doing an if test. So sort of the standard thing. You have to do something to break the union out. Yeah, intersection union types kind of depends whether your head's right side up or upside down. If you're in Australia, you might call it the other way.
Exactly.
And yeah, people use all kinds of shortcuts. So as soon as you have that concept down, then there's all these shortcuts you do to say, I have a type system shortcut that says this type cannot be a null, or can be a null. Like by default, it cannot be a null. If you want to allow nullable in the field, you put a question mark on the type.
Yep.
If you do an if statement, it immediately removes the null because it's a null check, and so it gets rid of the null right away on the tested branch, and all the usual shortcuts apply. And then there's shortcut operators that say do all these things, but if any one of them's a null along this chain, you get a null out, and you don't NPE along the way. You just abort prematurely.
Right. Turns out that the only place we actually had to respect null as a runtime understood value is in equality checks, and that's just to make the language not suck. Because if you want to compare something that's nullable with something that's not nullable, like you want to compare a nullable string to a string, generally speaking, we wouldn't allow that because the two types are not identical. So types have to be equivalent to be comparable.
And you made a shortcut for null.
And we cheat for null, yes.
Yeah, okay, fine. No, I'll let you compare any two things, and if they're known to be the wrong type, the test just says, well, they'll never be equal, so no. That's a typing time known false branch.
Right. Yeah. Equality is one of the most challenging parts of
there's a different question similar to null that's equality or not, which is When do you do deep equality? When do you do deep pointer? When do you do pointer equal? You know, strings are interned or they're not, so I can compare strings with pointer equality or not.
Right. And left associativity is another big issue.
Really?
Yeah.
Big
So
issue.
in Java, if I say if A equals B, I get a different answer from if B equals A.
Wait, if A equal B, really?
Yeah.
Why?
Because A is a sorted map and B is a hash map.
But they equal.
No, because a sorted map checks order.
No.
Oh, sorry.
Equals reference.
Sorry, right, I forgot. Yes, if you're checking reference, they're never equal.
Right, that's what I was talking about. If you're doing dot equals.
Well, so we don't have dot equals and we only have equals.
Okay, I have to have equals because I'm trying to do some low-level things that are only going to work validly with equals being in the language. And if you want dot equals, you can get it with some other way to get dot equals.
Yeah, so we have equals on reference. So it's based on the type you're comparing. So if you're comparing two references, it's a pointer equality.
So I would claim you have that sounds like you have not everything's a reference, but instead some things are references and some things are objects. And that comes down to, you know, copy.
Everything is a reference, everything is an object.
Yeah, are you all immutable?
But some objects are identities. Some objects fit inside a pointer, some objects fit inside a number.
Okay. Okay. All right. We have to sort
because
things out.
we didn't want to give up. We didn't want to give up. You know, we didn't want to have to virtualize 2 + 2, right? We didn't want to have to virtualize if 2 = 2, right? So we still have all the performance benefits of reference equality, of you know, intrinsic types. It's just we don't have any intrinsic types. We have no primitive type system.
Gotcha. All right, so I'm a different direction. I have a primitive type system, but all primitives support all operators via operator overloading.
So your primitives are all objects.
If it's a primitive, it bakes down to a primitive. But the typing system knows that it's a primitive, and therefore you can say .hash and .shit on it or whatever, and that will just turn into the overloaded operator version of hash on an int or whatever you're doing.
Right. Exactly. So
yeah, the primitives are objects, but they didn't carry any object overhead, which I guess is where you say that you came through as well. There is a difference here in that at some point, if you mix primitive types in a collection, an array, for instance, then I will have to box. And at that point, you have to ask for boxing, or you get it for free and it has a cost. And it's a typing, that is a language typing thing where I say, in this region of code, boxing is not allowed. Tell me if I have to box or not. You know, pick your default, but the point is no auto boxing if you have performance code. You can ask for no auto boxing in performance code. And typically you don't have to auto box unless you're mixing it in a mixed collection of primitives of different kinds.
Not to switch gears, but I was wondering about sort of the IR and pass designs that you see in different language runtimes. You know, you have one model in the JVM where you know, you have a certain IR, certain optimization passes, certain things that happen when the code's loaded and then when the code gets hot. Then you have other approaches like, you know, what some of the JavaScript VMs do. Then you have other approaches like Shea Scheme with the NanoPass compiler, which is, you know, very, very clever, very fast, and easy to manipulate. And yet other approaches like Luajed, or, you know, there's all kinds of points in the design space. I was just curious about A, maybe the approach you're taking with your language experiments, or B, anybody else's approaches that
Yeah, right. So I give this talk on how to do virtual machines, and we spend some slides on this shit. You kind of have to make a call between only doing JITted code and doing an interpreted versus not. There's pros and cons both ways. And then there's sort of the IR question is a different one actually than the implementation. So you break those spaces apart, and people go both directions, both ways, all different versions. So there's an interpreter or not, which there's a lot of run once code in the world, and you'll never beat an interpreter on run once code. And then there's you have an interpreter and you have compiled, you almost surely have a real pain in the neck to cross between interpreted and compiled code. That hotspot worked out, and it's similar to optimization, deop, reop thing that Cameron was talking about earlier. You have the issue that it's nitpicky, super detailed, but there's a finite amount of grief you have to go through, but it's hard to find all the grief points. It takes a little while. Once it's done, it's done. Then you can mix between interpreted and compiled. Having said that, you can skip all that grief by having only compiled frames. And then the compiled frames for a lightweight version and a heavyweight version can handshake pretty cheaply through the same stack frame layout, and there's no real overhead calling between the styles. That's on the implementation side of things. On the language side of things, I see people go all over the map for what to do with IRs. Long ago, I went for graph-based SSA and loved it, and that's what Hotspot uses. For the C2 compiler, C1 does it as a different version of things.
So what was the acronym again? I didn't.
SSA, static single assignment. If you're into compilers and you don't know what SSA is, you should go read up on SSA. It was the largest single change to compiler technology in the last 20 years. So 20 years from Fortran to, I don't know, 80s or 90s, and then SSA came along. As far as I'm concerned, that was the largest single change to compilers. The Grail folks picked it up. Sea of Nodes is just basically SSA all the way. So what it means is I can represent the program state as a graph, literally, as opposed to a collection of tuples, as a control flow graph with a list of things in a basic block, as a bunch of other versions of things. That becomes just a complete flat graph, and then the optimizations against it are sort of trivial graph rewrite rules. So very straightforward to run all your sort of theoretically high-end optimizations. They all have fast linear time. Yeah, SSA book, boom, there you go. Someone's threw it in the chat. It's a great form, in my opinion. So I'm using SSA again for what I'm doing. Having said that, there'll come a point where I boil SSA down to a control flow graph with nodes, but same as I did for Hotspot, it'll be SSA even down to machine code generation. So that's what you're gonna do with code gen. If I end up spitting out bytecodes, and I probably will for first pass, I will still be SSA right down until I spit out wherever I give up and hand it off to the next layer will be SSA down the line. So I know other folks do it differently. It kind of depends on your language format. I believe many of the JavaScript guys do a first pass similar to maybe some interpret, but I think some do.
So V8 is Sea of Nodes.
Yeah, I knew, and then there were heavyweight with Sea of Nodes. So there's a lightweight first pass, and then there's a Sea of Nodes. I knew that with V8, and I think some of the other guys have done it as well. So I would claim that the modern high-end implementations seem to be heading towards Sea of Nodes. Having said that, anything that's even slightly older and or being simple and you don't want to deal, people do whatever's convenient, including build an abstract syntax tree in AST and do some shit on it to clean it up and then walk it again to go spit code out. It's a great first pass without any thinking. The SSA is, in my opinion, just as easy and just as fast, but it's a different way to look at the code. And so you have to wrap your head around SSA form. Okay, here you have the big pause where, somebody can chime in. There's a bunch of new people here.
Cliff, I brought this up on Twitter some time ago. So like maybe one of the ideas, things we could discuss is, your approach to working on a problem. Like if, your language or whatever, do you go out and read papers? Do you, how do you think things through? I mean, like, because, writing compilers is hard. I don't know if you can just like jump into it and, maybe that's it, but.
Well, okay, so I jumped into writing compilers when I was 15. That was a long time ago. So there's a lot of jumping into compilers that has come and gone, water under the bridge for me. If I looked at, like, in recent history, I jumped into machine learning and parallel language design. I've jumped into concurrent, super highly scalable data structures. I've jumped into financial markets. In all of these cases, there was a jump in where I did a quick run through. No, sorry, my cat has come to beg off. Hey, Lisa. Crap.
Put him on. Put him on.
Well, she just got her hair cut, so she looks ridiculous in my opinion. Wow. Okay.
It's better than me, considering I haven't got one.
It's, standard lion cut on a fat cat. Very fat cat. Yeah, great. Okay, yeah, no, my turn. Boy, both of our cats are like more like dogs than cats. They'll come when they're called. They know their names. They beg for scraps on the table. It's ridiculous.
Cats are great. Yeah, I love cats.
Yeah, okay, so jumping into new things, like all the books, you need the books for the sort of the high theory and the deep understanding, and that's how you're going to make a significant impact. But you won't get any knowledge. Oh, here we go. So I've got some competition over here from Frank. But you have to have a basic understanding of what you're trying to do and what's important and what's not. And for me, the basic understanding comes from a try and screw up. So, same as like running a startup. You've all been ready to run a startup all your life. You just don't know it and you didn't try. So you have to go try. I mean, some of you have, I don't know. But the point is, a whole lot of people say, I'll do it when I'm ready. And I'm going to get ready, and I'm going to get ready, and I'm going to get ready, and I'm going to get ready. And they've been ready for a long time, and they're still getting ready, and they never do. Right? So you just pull the trigger. So you jump in, and you attempt to write one, write a compiler, do whatever you're going to do. Write an ML algorithm, and you screw it up. And then you understand what's hard about it. Right? At least some state. And you have some lingo and some jargon figured out. Now it's time to hit the books. Look at the theory. What's come before you? What have other people tried and failed and tried and succeeded on? What should be straightforward and what did you just miss because you just didn't know? Oh, yeah, duh, there's some easy things. Then I hit the books. Yeah, totally. And then I go back around for round two with, with formal theory in hand. And, compilers, I did this a long time ago. I have a lot of deep formal theory. And that shows up in everything I do in my compilers. I don't have to hit the books anymore in compilers. But when doing machine learning algorithms, there was usually a first cut. There was some deep read of some papers, state-of-the-art bleeding edge papers about what was important and why. Because we were doing a parallel distributed version, and these are all academic write-ups with nice mathematical theories or mathematical notation, but not necessarily any notion of how you would parallelize it and how you run it actually, and what issues you really saw in the field. So the usual story is your data quality sucks.
H2O?
I'm sorry?
Is this for H2O?
Yeah, H2O. But I did the same kind of behavior when I did like big parallel scale out for Azul, where I tried doing a bunch of things and I kept hitting bottlenecks and I kept hitting race conditions and I kept hitting whatever. And I finally sat down and did a little more formal theory and decided I needed to be doing state machines. And I did some state machine read-ups to see if there was something, and there really wasn't much to help you write a state machine in software to run in a widely parallel box. But there was enough to get some theory done, and I ran through, and one part of the theory was knowing that you had to cover all the states, because you were going to hit them all, even if you didn't see how you're going to hit them. And then you had to interpret what that state meant and how you would deal with it in the code. Once you sorted that out, the state machine writing was easy. Suddenly I had non-blocking hash map, and it scales linearly to any count of readers and writers. And in theory and in practice, it scales linear to thousands. right? So it's a nice piece of work. Same for H2O doing gradient boosting machine, right? Random forest, our first cut sucked. Looked great on paper, is a nice data science systems engineer implementation. The mathematics sucked. We blew it on the math side without realizing it. Once you understood the math, you had to slice and dice the problem a different way. We built a random forest to get good answers out and also be scalable and distributed and blah, blah, blah. FinTech market, much the same kind of thing. What the hell's going on? I had an expert tell me about FinTech. I knew how to do data science and how to do big data. And along the way, I learned what the hell's going on and why the markets are the way they are and basics of how they function. So in all these cases, there is a first cut to understand the problem space that often had fails in it. Some success, some fail. And then there was some formal theory learning phase. And then there was go back with formal theory in hand and try again.
Yes, I'm working on a open source GraphQL to SQL compiler. I mean, it's very high level thing, but it's kind of how I approached it too. I just kind of like started off, and honestly, I'm not a compiler person. Worked on like ads serving engines and stuff, but not compilers. And so yeah, I just kind of, and I think reading the Go source code really helped me because that's kind of like super readable.
Oh,
and
cool.
now I'm at the stage where I want to like read some papers and maybe improve the fact that I'm doing so many passes through the AST.
Right, you're doing ASTs, you can pass after pass AST. So what SSA is all about. All the passes become one. I have one giant. It's not really giant. I have one pass, kind of.
I have that link open, so that's my going to be reading.
There you go. There is a cleanup pass that's the complete total much optimization pass. Then there's a point where I respect that there's execution frequencies and loops. And that's a different kind of a pass done on SSA. And then there's definitely a walk to go spit code out. So there's more than one pass, but the actual bulk optimization happens in one pass, and then the loop cleanups are a separate pass.
I have a general question, implementation question. I don't know this, obviously I could benchmark it, but just from your experience, maybe having an AST as like a graph with walking pointers as opposed to like using like an array? Like, I don't know. What is your experience? I have used an array because I thought it was more optimized. Optimized without actually.
Right. So premature optimization is the root of all evil. Yeah, usual story. So the main cost these days on processor speed is being out of cache. So size matters. Having said that, premature optimization is the root of all evil. You should write what is convenient and easy to understand and get it right. Then discover that you suck for speed and speed it up. If you know from up front that you just must have speed in the first place, then you might make some initial design choices like SSA versus ASTs. But if you don't know how to write a compiler, AST is a fine start. Get it right, then get it fast. Don't bother with speed questions now. Pointers are easy, do it with pointers.
Yeah, I'm kind of balancing
pointers to small ints and do an array-based version for size. That'll probably give you a tidy speed up. So will a better algorithm. Better algorithm will give you better speed up all around.
True. My thing kind of runs sometimes in the hot path. So it's almost like a request comes in and it does this. So essentially, I'm also kind of balancing allocations because Go has it is a garbage collector language. So I don't have extensive experience in that the Go garbage collector, but less allocations is better. So.
Yeah, I don't either. It is the case that high volume allocations present a fairly large hidden cost. The bump pointer allocator is cheap. The garbage collector on things that die fast is cheap. Leaving out of memory bandwidth, because everything you allocate is guaranteed not in your cache, is expensive, but won't show up on any standard profiling technology. I can demo this fairly straightforwardly. Sometime on one of these things, I could spend 30 minutes and show people a 5x speed up on a single threaded application that's only reading 2 gigs of data from FinTech data and doing simple math by removing allocation. Although at the time you do it, the GC cost will report it as essentially zero. And the profiler will just put profile bits all over the map saying costs are everywhere. Nothing's obvious except the obvious loop over the 2 gigs. You'll get no indication that the DC is the issue. And yet getting rid of DC will give you a 5x speed up. So it's real. Having said that, still get it right, then get it fast. And then this guy's putting out this thing that says fee nodes versus blocks. Start with it. If you're doing SSA and you haven't done before, start with fee nodes because it's obvious and you understand what they do. Blocks are conjunctions of fee nodes for efficiency. And again, you know, get it right and then get it fast. I still have fee nodes, but I can get it to all my member fee nodes in one pointer indirection. So I effectively have a block-like effect for the cost of a pointer indirection. I have an array of pointers to fees at the blockhead because that's what you hang off of a region node. And I can walk them all as an array of fees. So it's not an inline array of fees as an inline array of objects. It's an array of pointers. It's a little more indirection costs. And again, you know, I'd say profile before you bother to speed that one up. I do have an API that lets me get at my member neighbors for cheap. So that I have an API that you get out of a block argument API. It's just not implemented. It's implemented as raw fee, so I can also have a fee too. So kind of, I'm aiming for the best of both worlds there.
Another question I had was, I don't know, could you share some experience on high frequency, you know, programming in the high frequency world? It's, you know.
High frequency trading? You're talking about low latency trading?
You know, working the West Coast, I don't have much experience with that, so.
There's high frequency trading and there's low latency trading. I did a modest amount of work. I basically talked people through, and there's a different question from Gotti. Save your question, Gotti, and bring it around again. I did a modest amount of work for for low latency guys, mostly explaining to every freaking trading firm in Chicago and half of them in New York why people use Java for low latency trading without actually doing the low latency trading. I myself did a lot of looking at high frequency trading. And the difference is high frequency is not attempting to beat the other guy to the punch. It just means you're doing a lot of trades in a row. So the low latency guys have this race that they front run. The leader gets wins all the marbles and the losers lose. The second place is, big negative and the winner wins all the marbles. So kind of a winner take all, and in that kind of a world, the nanoseconds count, people do these amazing games, and we all heard about it. Having said that, there's lots of folks that do that, been doing it for a long time. That market's mined out. It's well known right now, if you dump a big order on the market, all the front runners will grab it, and there'll be front runners right behind them, and the market will stabilize within a millisecond over the price. And there'll be some initial hit that somebody will get. So people usually have a big order, they dribble it out over the course of seconds to minutes, not very long. And the market stabilizes pretty rapidly to for that big order hitting the market. Sometimes it's called a whale. It's a giant order hits the market. You can imagine the market sinking rapidly because it's flooded with too many orders that no one cares for. So the price drops real fast. If you're selling a whale of a deal, you don't want that to happen. So you work around it. And the obvious thing is you dribble your stuff out and people snatch it up as they see fit. And the high frequency guys still get their margins, but that's not as big as it used to be by any means. Sorry, the low latency guys. The high frequency guys is a common trading technology that's just simply, we don't want to hold on to anything for any length of time because that's a risk factor. We want to take our profit and get out. So they hold on to stocks for milliseconds to minutes, and they churn a lot. So if you're looking for fraud in this kind of a market, you're looking at, millions a day, billions. A big top 10 bank will have 1 billion transactions in a day. And so I'm running AI on 1 billion transactions, and that was me doing fintech stuff for AI. But mostly what gave us problems was the high frequency, not low latency. Low latency guys have sorted themselves out some years ago. People got annoyed, people got mad, but it wasn't anything illegal. It was just a new tech, and the market
Are they on
just
Java?
the presence of the new tech.
And are they on Java? On the JVM?
At the time, so a decade ago, about half were. And like I said, half were on it and half wouldn't know why the hell these guys would be on it. So I talked to both sides, and the guys who were on it did it because they can flip algorithms easier.
Yeah, so Goldman was the most famous of the front runners, and they were all Java.
Right. Once it's JITted, the code's, like I said, it's as good as like, GCC-02. It's pretty reasonable stuff. You had to get past the jitting hump, and you wanted to be past the jitting hump at the start of the market day. So when your new algo, which you've never run before, has been loaded into the JVM, which you're just starting up, and the market hits, and you don't want to be jitting at the milliseconds when you just want the thing to go. So they had a couple different technologies they were working through. Azul's directly addressing that with their Falcon project. Pre-warmed in a lot of ways was one of the things they did. Leave it up overnight, except they had GC issues, so they had to not have a full GC during the course of the day, or they had to reboot at night. Where everyone did all this shit for how to deal with allocations and how to deal with jitting. But they made it work, and in exchange, they wrote their algorithms in Java, which let them test and debug and straighten them out a whole lot easier than C guys who would test and crash and burn endlessly till they got it right. So they were moving a little faster, but they had to do a bunch of work to make it support the speed they needed when they needed it. And that's why the C guys were confused, because it wasn't always fast. And they had this rumor that it wasn't fast. But in fact, once you get past the jitting hump, it pretty much is identical. If you write C-like code, you can write ugly Java, you can write nice looking Java that turns into ugly C code that runs poorly. But if you write C-like code in Java, you get C-like performance out. And you can still get range checks, and you can still get allocations when you don't care. And the hot path, you write the C code the way in Java, the way that it needs to be to go fast. And everything else is just like regular Java code. It doesn't have to be fast, it just be convenient and easy, and it's way the hell simpler. So there was a market for those guys. Both high frequency and low latency were doing it. And then the other side of the market was like, why the hell are you doing it? So it was a fun time, but I haven't had those conversations in 5 or 6 years. Does that answer?
Can you give an example of what you...
Okay, somebody's trying to talk and they got no sound on their mic.
It's me. I'm trying to talk.
Is it Prashant?
Yes, that's me trying to talk.
Yeah, that's better, okay.
My question was, can you give an example of when you talk about C-like code, can you give some example of that, right? So for example, Java does not have the ability to pass by value, and they seem to be working on it. But like in the current JVM that's out there, what would you call something that,
well, it's more like what's not C-like. So if you're writing low latency code, allocations are bad. Mm-hmm. So autoboxing is bad. Mm-hmm. So you better not, damn it, autobox. Mm-hmm. So how do you turn off autoboxing? Right? Give me an error, a type error, if you would otherwise autobox. That's what I want. That's what these guys needed. So they had to deal with that. Don't allocate except carefully, particularly any hot loop over anything. Doing X a billion times, where X is anything expensive is your expense, and allocation a billion times is the death knell. So thou shalt not allocate when running a loop over a billion things. And how do you code that way? It's not hard. C guys do it all the time. Do it by default. Do it naturally, because that's how the damn malloc-free kind of works. You do the same kind of technology when you're writing Java code. You pre-allocate before the loop. You run the loop reusing the memory space you saved beforehand. And when you're done, you can walk away. Then you don't have to free it. But if you're allocating in the loop, you suck by big numbers. Don't take virtual calls unless you really want to. Know that you're taking a virtual call that's actually virtual. But if you have just regular old Java calls to regular old non-overloaded methods, they all inline properly. They're all static calls. They all do the right thing. So that's all fine. Arrays are fine because the range checks typically the the range check gets eliminated, or the cost is super low anyhow. If you're doing one-off, I don't care on the range check, it's free. If I have a million in a row, it got eliminated, and again, I don't care. There are uses of arrays where the range check will cost you a noticeable amount, but you have to try hard.
Mhm.
And one of them would be, I have a lot of short arrays that I never visit ever again, that I have to range check the first element, and I have to get the element of interest, and they're on different cache lines. So I have arrays of length more than 32 bytes, 64 to 128 bytes long, that I touch once and never again, which would be true if I have an in-way binary tree, where I walk a tree randomly every time, and I do an inf array. I get one cache miss for the array length and one cache miss for the array element to go to the next element down, but it's a giant ass pile of data that I'm doing a binary search on, and I get double cache misses all the way down the line.
Or a trie.
Yeah, a try, right. You can make a try short, and it doesn't do that. You can also do try a couple different other ways that doesn't do that. But if you kind of sort of default your way to an alphabetical try with letters of the alphabet, you'll do that naturally, and that will cost you some performance. Other things, you just like, you know, mostly it's all same code, same stuff. Don't use, my personal take on code that I want to be performant is that I will disallow getters and setters in hot code, because I don't know what that function call does without looking through it. Because I don't know, I have to pay attention, and that removes my brain from understanding what the hell's going on in the code. So I know getters and setters in hot code, and no getters and setters in concurrent algorithms, because I have to know every memory touch. I have to see the memory touch in the algorithm to know that it's correct. So I very rarely do getters and setters. There are places where it makes sense if I have an API that I know that I want to deal with it that way. Hot code, no. Concurrent code, the API is very different.
Getters and setters are not eliminated anyway.
There's a couple issues there. The getters and setters are eliminated almost always, except when they're not, and then you suck. And when are they not? When you've overdone your inlining budget on a particular compilation. At some point, the compiler gets tired, says it's too much, and I quit. And we try Hotspot, Hotspot tries really, really hard to get all the getters and setters, but there is a give up moment, and you can fall into it, and we totally have done so, and I don't know if that still happens. I see Charlie is nodding his head, yes, you can still fall into it. Okay, so that it always happens except when it doesn't, and then you suck. And the other one is it's the intellectual overload. I'm looking at a pile of code. I know for a fact this code must run fast. This is my hot problem of the moment. What is this function call doing? Oh, it's a getter. Okay, it does nothing interesting. I need to go look at other things. I just took my head away from the problem of what this loop is doing to go sort out what that function call is doing. I want to see a bare method, bare instance field, bare field, not a getter. So that I know for a fact that this is like a trivial thing that I'm going to get loop hoisted, loop invariant, just one bounce through. If I'm counting cache lines through my loop iteration, it's just one more cache line or whatever. I don't know what that function call does. I have to go look. So no getters and setters in hot code because of the mental overload, and there's a rare risk that you'll fall into the pothole of it didn't actually inline and then you suck.
I've always wondered what the when you do an instance of like A instance of B, like is that an expensive check? What does it do? Like, is it like just a check on a bit field? Does it do an and or or? Like, how?
I'm sorry, what is it? A versus B, like an instance of test?
So like if I have an object, an instance, I want to check, you know, if this object is an instance of this class.
Oh yeah, instance of checks are generally one clock cycle.
Mm-hmm.
One clock cycle.
Wow. Okay.
It's a load compare branch. Mm-hmm. The load is from the object header, which is usually in your cache. So it's a one clock cache hitting load. Mm-hmm. The compare almost always is correct. Mm-hmm. So the compare is predicted by the x86 almost 100% of the time, and the branch is predicted then after that. So it's usually one clock. If you do complicated interface lookups, they can get expensive. Mm-hmm. If you have irregular types that you bounce around on, the prediction may not be correct every time. So there are times when it's not one clock, but if you're just writing junk code where the test never fails and you just have to cast, it's one clock cycle.
And For like array range checks, I know you were talking about that earlier. Is the length always stored with the array, or like for
Yes.
really short arrays, you always sometimes just calculate it or something?
No, the length in Java, the length is always stored with the array. It is a guaranteed part of the object header.
And with
So
that,
you have a mark word, a class word, a length field, often some alignment padding, and then your field values, your array values.
so every time I access an array, am I also spending one extra clock cycle at least to do the range check, or is there sometimes that
the range check costs are, there's always a range check. They are often bulk done for walking over an array. If you ask for one element of an array that you've never asked for before, yes, you will also ask for the array length and check it. The check on the array length is a different cache line sometimes than your object, and that is the cost, not the actual check. The actual check is 1 clock again.
Okay.
But it's a different cache line, it's a different cache line. Having said that, if you're walking a large array, and anything beyond 10 or 20 elements, this amortizes out already, the range check is done once in the beginning. We ask the loop, what is the max value the loop will ever test?
I see.
We check that, it's valid, we run the loop.
I see. Cool. I did not know. That's really cool to know. Thank you.
Yeah, and that's been around for 25 years. That was one of the early things that went in.
Well,
Everyone knew you had to do range check for safety. Everyone knew it was going to be expensive, and so we made it not expensive.
as long as the loop is analyzable, you can always write loops which you cannot do this kind of trick with.
So the limits are the array index has to be a classic induction variable. So we use the strong version of finding induction variables. You have to have an induction variable. It has to have a property that it's monotonically, it has to be stronger. Okay. It has to be incremented by a loop invariant value for a trip count that is maximally known before the loop starts. So none of these have to be constants. So the loop is running from a lower bound n to upper bound m by striding by x will range check it.
Does this work for Java lists, by the way?
Nope. Lists suck versus arrays. As soon as you get past like 3 or 4 elements, you're better off with an array list. It's another one of the fun memory bandwidth versus performance classes I teach on.
If you really care about performance, then you should prefer array list over regular list.
Absolutely. If you have 0 or 1 or 0, 1, 2 elements, you can contemplate a list. If you have anything beyond like a handful, you want to.
Do you mean list, like a linked list?
That's what I heard.
Yeah, you should never, ever, ever, ever use Java's linked list.
Oh, sorry, list, like java.util.list.
Yeah, list is fine. Array list is a list, yeah. But never use linked list.
How do you know the upper bound of a list except with a
linked list or an array list? An array list, you know the upper bound, and a linked list, you do not.
So with an array list, then I've looked at bytecode before, and it looks like it. Dang, I already forgot.
Look at the source code for array list. It stores the length directly in the class.
Oh, but my question is, can the optimizer? I'm going to trip over my question, but figure out that you only have to eval the size of the array list once.
Yes. So your loop is over an array list. Your loop is typically for I equals 0 to the length of the array list. He range checks the length of the array. He does not know the invariant, but the length of the array list and the length of the array are monotonically set. And he might now, I don't know. At the time I did, he did not. So he ran a loop from 0 to the n value from the array list field and limited also by the length of the array. So he basically took both of those fields out. He does a min and runs a loop over the min. And then if you have more iterations left over, you throw a range check exception. So the cost was, I loaded an array, you starting from an array list, you load the array field length, you loaded the array itself, you loaded the array length, you checked these two with the min, and then you started iterating fields and the other guys. So it was typically a couple cache lines to go get those things and no more range checks other than the beginning one, you're done. So array list is the performant one. Linked list is not performant Java util list is an API that supports them both. Just go allocate instances of array list, not linked list.
Yeah, so my question was, does, I guess with an enhanced for loop over an array list, can you get rid of the constantly checking the
Yes.
condition?
Yeah.
Oh, okay. Cool.
Because it's the same as using an array. It's just that there's one more level of indirection that the analyzer has to go through.
But the analyzer can
It
it's
totally,
smart enough to.
It can
totally
inline
goes-
it the same way it can inline your code.
Yep. Identically analyze. The Java bytecode spit out the damn whatever, the damn object for the iterator, which the analyzer totally inlines sees through. Because it's a common thing. It's been around forever and a day. I was doing that before we had smart iterators, because people were writing these other kind of iterators that not over enhanced for loops, and you had to do it for those. So that happened a long time ago. All right, I'm going to grab something from chat here. Blah, 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 blah. Back here. Oh, okay, no, this has probably all been answered. Or tracing JIT's done, but I think Gotti left. He dropped off the call. Or tracing JIT's done? No, I think they have an obvious place in the world. Had experience using support for dwarf in JITted language. Oh, in JIT, not both. I did dwarf a long time ago. I've done JITted more recently. I've not done dwarf and JIT. And I honestly don't know. I'd have to stare really hard at the dwarf spec again to see if it covers the right set of bets.
Well, we at Azul was found where we use LLVM, we got dwarf for JITted code. We translate, so we collect this information for mapping profiling ticks back to Java stacks. Although internally we convert this into more compact representation on the VM side. But for debugging purposes, when I'm analyzing, looking at the code, I have an option of generating an object file for a particular compile and then looking into dwarf there as well. So it can be done. LLVM does it for us, but I don't see I don't think that we get much out of it.
You hooked a further end of the tool chain is what I heard, which sounds useful. No, there's a usefulness to bringing up some of these old tools work really well. So there's a usefulness to having them enabled. So it sounds like the answer is yes, it can be done. I don't have any support, but it can be done. Somebody did it for Graal.
I'd love to learn more about Archer's experience in this. You had mentioned you're unsure of the value of this form of support. In general, we're working on debugger toolchain. It would be incredibly useful because then we could leverage all the technology that we've built for native code for JITted languages. And in today's ecosystem, basically for every JITted language, assuming there is sufficient observability, we have to hook into some kind of FFI layer and extract information from there. And typically it's less structured and not as expressive in any way as dwarf.
Well, I think you still have to cooperate with the VM somehow, because it's up to the VM to install this particular code at particular address. So, and this can change, code gets unloaded, loaded. So there will be some interaction with the VM. I think theoretically, we can add dwarf into this interaction. So when debugger asks the VM about some addresses, the VM can spit out dwarf and say, yeah, well, you can look and explore, but there still will need to be some extra interaction. So it won't be as if you're looking into statically compiled binary.
Gotcha.
So yeah, and as I said, when we use it, we change the representation. We get dwarf from LLVM, but then we produce our own internal representation just because it's more compact compared to what dwarf has. So I don't think that we want to have it enabled on by default, but with some extra flag, I think we can have it.
Gotcha. Thank you.
Yeah, also it might be useful. We can have dumps of compiles and we can dump object file for every compile, and you can look at the object file using standard tools. I don't know if it's as helpful as online debugging, but at least it's helpful for analyzing the result of the compilation for a compiler developer.
Gotcha.
I'm going to answer Cameron's comment in the chat. Yeah, I think the virtual, non-virtual thing has been solved. Everyone agrees that calls can all semantically look virtual and pragmatically be static for performance, and we have the best of both worlds, and that issue's been solved now.
That's
So,
my
yeah.
assumption.
Yeah. I'm in that boat. I mean, I'm going to go that route as well.
Hi guys. While we talked native image, do you have any opinions on ahead of time compilation and compiling to a native executable as Graal does, or as it's in the JDK, I guess 13 or 14? Do you use it, or what are your thoughts about it?
I do not, which is fine. But I certainly have all my life. It's a fine thing. And I know there's a lot of low latency traders who are excited about this technology.
Well, I think there is this trade-off between peak throughput and startup time. I think in many cases with these statically precompiled images, either you have this ability to compile dynamically and restore peak throughput, but then you still have the JIT with you and it's not as small, or you have a small native binary, but then you probably are not able to specialize in runtime, and you're probably not able to reach the same peak throughput as an adaptive system would do.
Yeah, the adaptive system can be asynchronous as well. The design that we have for clients is to have the statistical collection in the baked in, but the JIT not baked in. So basically it collects the statistics, and then there's a daily build. So every time you go to upgrade your application, you get something that a compiler worked on for a couple hours to make faster, based on 1 million different people using it.
That's an interesting take.
Yeah, I actually suggested this to Gil last time I spoke, like a week ago, something like that.
Yeah, okay. So this is, you're talking about, you're running together profiles from all users.
That's our design, yeah.
Yeah,
exactly.
Yeah, okay. Yeah.
And that way you don't have to have the issue. Some of the platforms really frown against you doing dynamic compilation on the fly. So it kind of addresses that. So your first build really sucks.
Well, okay, define really sucks in terms of performance changes over time. I'd love to see the curve, the daily build performance curve.
Well, I mean, it's hypothetical at this point, but the idea is you're collecting a lot of unnecessary statistics, and nothing is optimized. So. Yes.
Just for people's curiosity here, all this collection that Hotspot certainly does, it's like less than 1% performance overhead. So this is essentially free. And so in my opinion, you should just automatically grab it because it's so useful for things like what you're talking about. It's also useful for statistical debugging properties. How often does X happen that I crash this often? I've used it in a variety of unusual contexts, but the data is almost free to collect. So frickin' you should just collect it.
You were gone all day.
Oh, there you go. Yeah, in the chat. You can, talk there, Matt. You don't have to actually write it out. It's all good. So in Forensic, the startup I did in the fintech looking for fraud, we ran together the AI models were built from data we gathered from all the clients all at the same time and ran it all together. So we weren't allowed to share any of their raw data with each other because that would be a horrible breach of privacy. But the model was built across the sum of 20 different trading firms. And then every trading firm got the model that was built on the other trading firm's data. So they were all excited to have, if trading firm X took a hit from the CDC and a fine for some illegal trading, they wanted to know what the hell that guy got hit with. So the model, the next day, the model would have that hit baked into it. And so they could get at least detection of the same shit that got the other guy. So they were all excited to share bad behaviors and how you catch it, but they were not willing to share the underlying analytics, the underlying raw data, sorry, not the analytics here, not the raw data. So I can imagine that you have an issue there too. You have to talk through your clients there, Cameron. I have some underlying low-level statistical data I'm collecting. You're collecting in your runtime. If it has anything that can be sort of represented, represented back to somebody outside the company that's readable, like names of functions, there's a security risk.
It's opt-in. It would have to be opt-in only.
It has to be opt-in. Yeah. We were very much opt-in, and you signed the contract with an opt-in interface. But for what you're talking about, you have to have opt-in. Yeah. And probably a discussion among what kind of data you're collecting. Are you collecting function names? I mean, I don't know. Don't tell me. I'm just saying. If you're collecting names of any kind, there's an issue. Because people write, cool shit in names, like the name of the machine learning algorithm I'm using to go spot this particular kind of trading system. Hey, I'm using neural nets to go do my trading. That's a key piece of tech, not anymore, but it was a key piece of, super secret stuff 5 years ago. So you gotta be careful there.
So, Cliff, I have a question. I've been working with a performance issue with the invoke interface calls. So basically, we use Scala and Scala collections. They have like lots of interfaces, and the way that traits are encoded as bytecode generates even more invoke interface calls. So yeah, I was wondering if you have like any pointers of like good approaches
sure.
for optimizing that.
Yeah, don't use interfaces.
Yeah, I have to basically optimize our Scala code phases. Yeah.
Right. I mean, I can tell you through where the fast and slow versions of function calls look like, right? So if you have a call that is analyzable with class hierarchy analysis down to a static call, which almost surely you do not, then it bakes down to like a static function call. It's all great. If you have a call that targets a single target all the time, then you get an inline cache, which bakes down to 2 clocks instead of 1 clock. That's pretty damn fast. If neither of those hold true, and by the way, you can have a single target that's an interface call. As long as it's a single target you're going to, you'll still get the inline cache. But if you have to have a real lookup, and the lookup is a virtual call, you get a load jump register. And the first load is usually free, but the second load's indirect off the first, so it can't make any progress. The third load's frequently a cache miss, and then you jump register, which is already not predictable very well, in like 30, 40 clocks. So it can be predicted if your x86 is seeing the same target.
The second load has been accelerated for the last couple of years on x86.
Oh, okay, fine. Okay, so that's
otherwise perfect. Yep.
But hang on. When you get to interfaces, though, there is a fucking spin loop to go look up the correct interface. That's just not going to go faster, and there's no reasonable technology choice that Hotspot can do to do the general interface lookup without a major rewrite of some core internal infrastructure. So interfaces calls that are megamorphic interface calls are just not going to go fast. So rethink how you do it so that you don't have to have a megamorphic interface call at the call site. And I talked through, I want to say Charlie Gracie, he's not here. I talked to a couple people over like JRuby or Jython about what their calls looked like such that the VM lost track of what the hell the static noon type was at the call site when he knew damn well it was a single target, but the VM couldn't ever deduce it.
Yeah, no, those are pretty simple.
Okay.
Those calls. Yeah. I've worked on Jython, and I'm close with the JRuby guys, and I know that the JRuby people had cases like that, and it was an interface, and it was always the exact same method even, because it was the same base class that was the implementation of that method for that interface always, and yet because it was multiple different actual classes that implemented this interface, because even if it was the same method, then it still became megamorphic because it wasn't the same type, because that's the only thing that it was based on.
Right. I thought those guys, you or whoever in one of those groups, I had this discussion a decade ago. They changed something and got some performance out that was interesting.
Check cost. So check for the abstract base class and cost to that.
Okay.
And do the invocation of that instead, and that works.
Okay. So there is a hack around. Did you catch that?
There is a hack around it. Yeah.
This is for Scala. Same hack. It's a hack.
Yeah.
But you do what you do.
The cases we have, it's actually cases where we have like actual invoke interface calls that are megamorphic. And it's even worse because Scala has lots of interfaces for collection. So I have the linear search on the interfaces that is like 37 items. So for instance, like I have a case where I have a collection that's iterating over. And just to access each element of the collection, I have 2 interface calls that need to go through 37 pointers of interfaces just to find the interface.
Yeah, and that's not going to get better because of the nature of how interfaces are defined.
Yeah, so I've made some progress on that. So on the just-time completion side on Graal, I use a few strategies for like optimizing cases where I have enough profiling information. So if like they all implement the same superclass, I can check like, is this the same superclass, or does it have the same vtable layout, and do it as a virtual call. But the case that I can't optimize yet is basically for the Scala collections. That is the worst case for us, where basically like the profiling information is not very useful. You have so many implementations. There's like 20 implementations of the collection, and you have like these really high number of interfaces for the implementation. So I was wondering if you has like any pointers.
Well, the obvious thing is that you use a virtual call. As soon as you iterate over a collection, sorry, let me back up. As soon as you iterate over a hot loop, over a virtual call or an interface call, you have a classic, you lost all your performance bug because you don't know what the hell you're calling out of the inner loop. So all possible loop invariant code motions and range stick elimination, all kinds of really cool shit that makes things go fast don't apply. You have to inline at this layer, not at this layer, right? So if this is 37 way, you need to make this 37 way. So this test comes here, and you branch to 37 loops, where each one of these loops has a static call to the Trojan target. And then you don't make 37 loops, so you want to make them lazily as you get to it. And then you get your performance. But instead of, I loop this 1,000 times, and each time I do 37 lookups, so I have 37,000 lookups. I loop 37 times up here to pick which of these loops, and then I do this 1,000 times, so this is 1, not 37. And the in cost is 37 plus 1,000 as opposed to 37,000.
I'm looking more for a generic solution for dispatching interface calls in general.
Yeah, and I'm up leveling you. This is what H2O had to do. You up leveled at the loop level, not at the hot inner loop. The best you can do in a hot inner loop is a table lookup, which is the load jump register game, and that's a virtual call if you can boil your thing into a virtual call. Otherwise, you have a spin loop inside of a spin loop, and then there's your n squared, and you suck. You know, you have 37 times your loop trip count, and you suck. So, you know, if you can teach somebody's analyzer that there's some interesting property that all the 37s all go the right way, you know, that's a code transformation you can go cook up and then produce bytecodes to do that. Or you can go into Graal, or you can go into C2 and go hack it in. But if you go into Graal and go into C2, you have kind of a major hack job going on to go make that work.
The other challenge is you're trying to use only a single pointer for that object. So all the pointers to that object look the same. So it becomes unoptimizable from a vtable point of view.
Well, that's why interfaces have that. Yeah, have that issue.
Yeah, yep. But if you can go with a fat pointer, you can actually apply the vtable optimization across the board. So I mean, it's still suboptimal because you've got the indirection on the pointer lookup, but it's a lot better than the spin loop.
Right. Can you boil that fat pointer just as another member field of the object?
Well, I think what you end up with is a ginormous vtable because it has to actually hold all the possible vtables that have been encountered for that object.
Vtables are cheap.
Yeah, because you have 10,000 of them, not 10 billion. Yeah.
Yeah, right. They're one per class, not one per object or anything.
One per type. Yeah. With interfaces, it's one per type, not one per class.
Okay, I'm calling an interface a class, but it's not, but it is.
It is. I hear you.
Okay. Well, we've been at an hour and a half. If anyone has got anything else they want to throw in before I, declare victory here.
You mentioned random forests a little earlier. We've done a couple of implementations of some fairly high-speed decision tree algorithms. What we found with random forests and gradient boosting was that if you really wanted to go fast, what you were doing is pushing irregular memory access out of inner loops. You could do things like vectorize and parallelize in your inner loops, but the real name of the game was trying to somehow be smarter than your irregular memory access. I was just wondering whether you ran into anything similar at H2O, or if you.
Well, you're talking about the execution cost or the model build time cost?
The training cost.
The training costs. I had to do it distributed. If you built a tree per slice, so in my world, big data meant too big for one machine. And therefore it's distributed. Therefore, not all machines saw all the data. If the tree was built on a partial slice of the data, it sucked, and that was a horrible random forest. Although it sounded great on paper, don't do it. It doesn't make a forest with shit. So that means that the data is distributed, but the forest is built on all the data. So at each layer in the tree build process, you do histogramming across all the data, and you run the histograms together with the log tree rollup. And then you build your new splits, and then you push the split out and go again. That was the major cost, was as the trees got deep, running the large histograms back and forth across the network.
Okay. So yeah, you're looking at it a little differently than we were.
If I fit on one tree on one node, we went down the one node approach and optimized it pretty well. Using sort of an update in place, split in place, where you recursively shuffle the data, partially sort, and then you split and sort and partially sort again. And as it fit in the smaller levels of cache, each sort you progressively sped up, and,
right.
So you got way the hell faster. So, it ran plenty fast for build, but you had to have all the data from all the nodes or you sucked. And that meant that you had to have network traffic, and suddenly that's the dominant cost.
Right, right.
So didn't matter. So instead, we did every possible thing to do smart histogram compression for sending it about. At the low levels of the tree, the histograms were all very small, and you didn't really care. But at the deep levels, you go down a random forest, you might go down 10, 20 layers. You go down 20 layers, you got 1 million splits. You got 2 to the 20th splits. So you have 1 million histograms, each of them very modest size. Suddenly you're slinging about gigabytes. And that's the cost. So we optimize that piece.
Mm-hmm.
Okay, I'm going to declare victory again. And I'm going to put a link online as soon as I can figure out how to do it. So this will all be public shortly. And I hope to see everyone next week. It was a fun conversation. Thanks.
Thank you.
Thank you.